Hello students, so the question here is match list with 1 with the list 2. The list 1, we have a series, that's the Lyman series, the Humphrey series, the Paschen series and the Balmer series. Similarly for the list 2, we have the reasons in which this series will lie. So we have to match this. So for the Lyman series lies with the UV reason. So Lyman series lies with the UV reason. So A will match with the 2. And for the Humphrey series next, it lies with the far infrared region. So it will match with the B will match with the 4th. And for the next series, that is the Paschen series lies in the infrared region, that is C will match with the 3rd. C will match with the 3rd. And for the D, that is a Balmer series, the Balmer series will match with the visible region, that is a D will match with the 1st. D will match with the 1st. So it's a theoretical question that is like mentioned in the NCERT. So the correct answer here is A 2nd, B 4, C 3 and the D is the 1st. That is a 4th option is correct. Next question, the maximum number of electrons possible in an atom having a n plus L value equals to 3 is. So for the n plus L value equals to 3, so what possible values we can put for the n and for what possible value we can put for the L. So the condition here is n equals to 3. In that condition, L should be the 0. And when n equals to 2, the L should be equals to 1. So here it is 3 plus 0, it will become a 3. 2 plus 1, it will become a 3. So when the L equals to 0, that means it is saying about a S. And when L equals to 1, that means it is saying about a P subshell. So in the S subshell, the maximum electrons possible are the 2 electrons, and in the P subshell, the maximum electrons possible are the 6 electrons. So according to the question, the maximum number of electrons possible, that is a 2 plus 6. So maximum electrons will be 8 electrons. So here the answer will be the 8. Next question, the shortest wavelength of helium plus ion in the Balmer series is X, then the longest wavelength in the Paschen series of lithium plus 2 is. So for the shortest wavelength of helium plus, first we will calculate with the shortest wavelength of helium plus. The shortest wavelength of helium plus 2, and it is for the Balmer series. So for the Balmer series, and the shortest wavelength we have to calculate for the Balmer series, the N1 will be equals to 2 and N2 will be equals to infinite for the shortest wavelength. N1 will be equals to 2 and N2 will be equals to infinite. And the formula is 1 upon lambda is equals to RH Z square 1 upon N1 square minus of 1 upon N2 square. So when we put the value for the helium plus, it will be RH Z square will be the 2 square. The N1 value here is 2. So it will be 1 upon 2 square and it will be 1 upon infinite square. Okay, so here this 2 square and 2 square will get cancelled out. So 1 upon lambda will be equals to RH, and the shortest wavelength of the helium plus ion in the Balmer series is given as the X. So the wavelength will comes out to be the 1 upon RH equals to X. 1 upon RH will be equals to X. So this is for the Balmer series and it is for the shortest wavelength. Similarly for the Paschen series, when we calculate for the Paschen series, so in the Paschen series what happened, the N1 value, here it is the longest wavelength mentioned, the longest wavelength. So for the longest wavelength in the Paschen series, the N1 will be equals to 3 and N2 will be equals to 4. The N1 will be equals to 3 and N2 will be equals to 4. So same formula we have to apply. It will be 1 upon lambda equals to RH, and it is for the lithium plus 2, so it will be 3 square 1 upon n1 square, that is a 1 upon 3 square minus of 1 upon 4 square. So when we will calculate this, so we will get 1 upon lambda is equals to 7 upon 16 of RH, and finally, like the shortest wavelength in the Balmer is this, then longest wavelength we have to calculate. So longest wavelength here, if you will see, 1 upon RH is equals to x. 1 upon RH is equals to x. So the longest wavelength we will get, that is a 16x upon 7. 16x upon 7. Because this RH, here we have related this from this equation, the first. So we finally get the wavelength as is equals to 16x upon 7. That is the option 2 will be the correct. Next question. The wavelength of the electron emitted by a metal sheet of work function 4 electron volt when the photons from EMR of wavelength 124 nanometer strike the metal plate, given the value of the HC equals to 1240 electron volt nanometer. So wavelength we have to calculate here. So first of all, the energy of the photon we will calculate. The energy of photon. So energy of the photon is equals to E is equals to Hc upon lambda. So the value of Hc is already given as 1240 electron volt, and the value of wavelength is given as 124 nanometer. So it is 124 nanometer. So it will cancel out and it comes out to be the 10 electron volt. Similarly, the next we have to calculate the kinetic energy. The maximum kinetic energy will be equals to energy of photon minus its work function. Energy of photon minus its work function. So energy of photon we have already calculated, that is a 10 electron volt, and the work function value is given as the 4 electron volt. So 10 minus of 4 will comes out to be the 6 electron volt. Then we have to calculate the wavelength of the electron emitted by a metal sheet of work function this when photons from EMR of wavelength 124 nanometer strike the metal plate. So in order to calculate the maximum wavelength, so it will be the lambda is equals to under root of 150 divided by its kinetic energy. So kinetic energy is, this will comes out to be the 150 divided by the 6, and on this calculation we will get it in angstrom, and finally when we will convert the angstrom in the nanometer, so final answer we will get as a 0.5 nanometer. So correct answer is option 4th. Next question is total number of radial nodes for the 4D orbital is. So radial nodes, the formula of the radial nodes will be equals to n minus L minus of 1. So here for the 4D, if we see the value of n equals to 4, and for the D subshell the value of L is equals to 2. So when we put these values in the formula, it will be the n is 4 minus of L, that is a 2 minus of 1. So it will comes out to be the 1. So the total number of radial nodes for the 4D orbital will be 1. So our answer will be the 1. Next question, given below are the two statements. The statement 1, the total orbital angular momentum of electron in s orbital is equal to 0. Similarly, the statement 2, an orbital is designated by the 3 quantum numbers while an electron in an atom is designated by the 4 quantum numbers. Based on these two statements, we have to choose which statement is correct and which statement is incorrect. So the first statement, according to that, orbital angular momentum is asked. So the orbital angular momentum formula is h upon 2 pi under root of L plus 1. H upon 2 pi under root of L plus 1. and it is for the s orbital, and we know for the s orbital the value of L equals to 0. The value of L equals to 0. When we put the value of L here 0, we will get the 0 answer. So the statement is that is the orbital angular moment for the s orbital is equal to 0. So that means this statement is correct. Now the statement 2, an orbital is designated by the 3 quantum numbers. So for the any orbital we have to define, we require 3 quantum numbers, that is a n, l, m. Okay, so for an orbital we require a n, l and m. N, l, m, that is a principal quantum number, azimuthal quantum number and the magnetic quantum number. Similarly, like for an electron, when we have to define an electron, we have to define a spin quantum number, that is a s. When it comes to the point of the electron designated, that is a s. So this statement is also correct. So both the statement 1 and statement 2 are correct. So our correct option will be option number 2. Statement 1 and statement 2 both are correct. Next question, assume that 2 into 10 to the power minus of 17 joule of light energy is needed by the interior of the human eye to see an object. The number of photons of yellow light with the lambda equals to 595.2 nanometer needed to generate this minimum energy are. So we have to here calculate the number of photons of yellow light. So the formula of energy of the photon E equals to NSC upon lambda. E equals to NSC upon lambda. And the value of Hc we will get as a 1240 electron volt. 1240 electron volt. So here energy is given as 2 into 10 to the power minus of 17 joule. So we have to convert it in the electron volt. So 2 into 10 to the power minus of 17 divided by 1.6 into 10 to the power minus of 19 will be equals to n into 1240 divided by the wavelength here is given as, that is a 595.2 nanometer. 595.2 nanometer. So when we will calculate this value, so n from here we will get n equals to 60. N equals to 60. So our answer will be the 60. So our answer will be 60. Next question, which of the following graph correctly represents the variation of particle momentum with de Broglie wavelength? So de Broglie wavelength and the relation of the particle momentum, that is a lambda is equals to h upon p. Lambda is equals to h upon p. So when we see this equation, lambda is equals to h upon p, here h is constant. So it is of the form, that is lambda is inversely proportional to 1 upon of p. That is, it is of the form y is equals to mx. Y is equals to mx plus c. That is a straight line. So here the lambda and the 1 upon p relation with the straight line having a 0 constant value. So this one is the state that is a correct graph is 4th, because this is like following the straight line curve. Y is equals to mx, which is of the form lambda is inversely proportional to 1 upon of p. So our correct answer is option 4th. The next question is the ratio of the time period in the first and the second orbits of hydrogen atom is. So the time period is t equals to 2 pi r upon v. 2 pi r upon v. So here if we put the formula of the radius and the velocity, we will get as a time period is directly proportional to n cube upon z square. N cube divided by the z square. So it is like orbits of hydrogen atom. So the value of the z will remain constant, it will remain 1. But the value of n is varying, like it's the first and the second orbit. So time here is directly proportional to n cube. So it will be the T1 upon T2. T1 upon T2 will be equals to 1 cube divided by the 2 cube. So it will comes out to the 1 upon 8. So here the ratio of the T1 upon T2, here the ratio of T1 upon T2 will be the 1 upon 8. So our correct answer is option 2, that is a 1:8. Next question, for an electron with the n equals to 3 has only one radial node, the orbital angular momentum of the electron will be. So for the radial node, like we have seen in the earlier questions, for the radial node, radial node, it will be equals to n minus L minus 1, n minus L minus of 1, and it is given as 3, so it will be 3 with n equals to 3 already given, with n equals to 3 has only one radial node, so the value of radial node is given as 1, so the value of radial node is given as 1 and the value of n is given as 3 and minus of L minus of 1. So from here if we calculate, we will get as a L equals to 1 here, L equals to 1. So from this L equals to 1 we have to calculate the orbital angular momentum. So the formula of orbital angular momentum, orbital angular momentum, it will be equals to h upon 2 pi under root of L plus 1, h upon 2 pi under root of L plus 1. So h upon 2 pi and the value of L when we put as 1, so it will be 1 into 1 plus 1, so it will be the 2. So we will get h upon 2 root 2 h upon 2 pi, root 2 h upon 2 pi. So it is matching with the option third. So our correct option is option third, that is a root 2 h upon 2 pi. Next question, the correct set of 4 quantum numbers for the valence electrons of rubidium, atomic number is given as Z is equals to 37. So atomic number Z is equals to 37, it is of fifth period, and its electronic configuration of rubidium is krypton 5s1, and it is asking about the quantum number of the valence electrons of rubidium. So for the 5s1, like for the s, the value of n will be equals to 5. This is the value of n, and for the s subshell the value of L equals to 0 and m will be equals to 0, and s having a 1 electron, so s will be a plus of 1 by 2 or minus of 1 by 2. So based on that, this we will match the option. So the value of a spin quantum number is given only as a plus 1 by 2 in all the options. So it is a plus 1 by 2. So it is 5, 0, 0 and 1 by 2. So it is matching with the option 1. So our correct option is option 1. Next question, which of the following is the energy of a possible excited state of hydrogen atom? So the energy of a possible excited state, for the excited states, the energy we have to calculate, like it is equals to minus of 13.6 divided by n square electron volt. And it is asking which of the following is the energy of a possible excited state of the hydrogen atom. So here the value of n can be 1, 2, 3 up to so on. So for the excited state of hydrogen atom, it will be n will be equals to 2. So it is minus of 13.6 divided by 2 square, that is a minus 13.6 divided by 4. So it will comes out to be the minus of 3.4 electron volt. So the possible excited state energy will be the minus of 3.4 electron volt, that is the option third will be the correct. Next question, at temperature T, the average kinetic energy of any particle is given as 3 by 2 kT. The de Broglie wavelength follows the order. So if we see the kinetic energy relation with the wavelength, so lambda is equals to h upon under root of 2mke. So from here we will see that the lambda is inversely proportional to mass. Lambda is inversely proportional to the mass of the particle here. So the lesser will be the mass, higher will be the wavelength. So in this question, like for the wavelength, like we have to see here the de Broglie wavelength. So the de Broglie wavelength is higher for the electron than the neutron. d Broglie wavelength is higher for the electron than the neutron because the mass of the electron is lesser than the mass of the neutron. Similarly, like it will be higher for the wavelength of photon. So the wavelength of photon, d Broglie wavelength of photon will be greater than the d Broglie wavelength of electron and then the d Broglie wavelength of neutron, because here the direct relation, inverse relation is given with the d Broglie wavelength with the mass. So our correct option will be the option number 3rd. Next question, if the shortest wavelength in the Lyman series of hydrogen atom is A, then the longest wavelength in the Paschen series of helium plus S. So first is the Lyman series. So for the Lyman series, so the Lyman series the value of, in case of the shortest wavelength, that is the n1 will be equals to 1 and n2 will be equals to infinite. And the formula, the similar question we have used earlier in the same phenomena we have used in the earlier question, that is a 1 upon lambda is equals to RH RZ square 1 upon n1 square minus of 1 upon n2 square. So it is for the hydrogen atom, so the Z will be the 1. So 1 upon lambda is R, 1 upon n1, that is a 1 upon 1 square minus of 1 upon infinite square. So from here we will get as a R equals to 1 by A, because it is given as the shortest wavelength is given as, so when we put here, so R we will get as a 1 by A, 1 divided by A. So this relation we will use in the later part, that is we will put this as a equation first. Okay. Similarly, like for the Paschen series, if we talk about the Paschen series, so in case of the Paschen series, and it is the longest wavelength, so here it will be the n1 will be equals to 3 and n2 will be equals to 4. So same we have to put in the formula, that is a 1 upon lambda is equals to R. Z here is for the hydrogen, so it will be the 1, and 1 upon n1 square, that is a 1 upon 3 square minus of 1 upon 4 square. And R we can put as a 1 upon A. Here R we can put as a 1 upon A. So while on solving this, we will get as a lambda equals to 7 by 36 of A, 7 by 36 of A, sorry, 1 upon lambda, here it will be the 1 upon lambda will be equals to 7 by 36A. 1 upon lambda will be equals to 7 by 36A. So the lambda will comes out to be the 36A divided by the 7. So our correct option is option 3rd. Next question, the electron in the hydrogen atom undergoes the transition from higher orbital to the orbital of radius, that is a 211.6 picometer. This transition is associated with. So based on the radius, we have to identify or calculate that this radius will belong to the which particular transition series. Okay. So the radius is given as, radius R is given as 211.6 picometer. So when we will convert this in the angstrom, it will become a 2.11 angstrom. And the formula of the radius, is 0.529 n square upon Z. Here it is a hydrogen atom, so Z will be the 1. So it will become a, radius is given as 2.11 angstrom and 0.529 into n square. N square, from here we have to, the value of n we have to calculate. So n square we will get as a 4, and so n will comes out to be the 2. And when the n is equals to the 2, so it belongs to the Balmer series. So the option is, fourth option is correct. That is a Balmer series.